In this video, we're going to talk about what makes a good nucleophile. So a nucleophile is a species that is attracted to a positive charge. So in the nucleus are the protons and the neutrons. The protons have a positive charge, so a nucleophile likes the nucleus. So we can say that a nucleophile is attracted to a positive, or in some cases a partial positive, charge. So as a result, nucleophiles are often negatively charged or neutral. So you might hear the term nucleophilicity. And this is the rate of attack of the nucleophile. So essentially it's how strong of a nucleophile or how good of a nucleophile that species is. And since we're in organic chemistry here, we can safely say on an electrophilic carbon atom, since everything is going to be carbon-based. So our next question is, what is a good nucleophile? And we're going to break it down into different factors that can influence that. And the first thing we'll look at is whether a species is neutral versus having a charge. So we're going to have to look at analogous systems here, but we can look at hydroxide versus H2O, and then anything analogous to that. So we could look at SH- versus H2S. We could look at the amide ion versus ammonia. And in all of these cases, the negatively charged species is going to be more nucleophilic than its neutral counterpart. That's because a nucleophile is going to donate electrons to the electrophile, so a negatively charged species will become neutral by acting as a nucleophile. So we'll say so if something is negative and it becomes neutral, the neutral version is going to be more stable and therefore less reactive. So we can look at analogous cases. We kind of have to be comparing apples to apples here to do this. And we can also look at the effects of electronegativity on nucleophilicity. So if, for example, we go across a row, we have, and I'm doing negatively charged species here, the amide ion, hydroxide, and then fluoride. In this case, the amide ion is going to be the most nucleophilic, and the fluoride ion is the least nucleophilic. So fluorine is the most electronegative atom, so it's most stable with a negative charge, and therefore the least reactive. Whereas the amide ion is fairly unstable with that negative charge, so it's going to be very reactive, and it will look to make a bond in order to become neutral. We can look at neutral species as well, so if we had looked at ammonia versus water, it would be the same thing. In this case, when these two species act as a nucleophile, they'll become positively charged. Oxygen is more electronegative than nitrogen, so it would be less stable with the positive charge. So I'm going to say here, least destabilized by positive charge that it would gain in acting as a nucleophile. So either the ammonia or the water would give its electrons in order to make another bond, and in doing that would become positively charged. Size is also a factor in nucleophilicity, and so here we'll think mostly about going down the periodic table, because that's where we see the biggest change in size. So we could look at, for example, I minus, Br minus, Cl minus, and F minus. So I minus is going to be the most nucleophilic, and F minus is going to be the least nucleophilic. And what happens is, as we go down the periodic table, these atoms get larger, and as they get larger, they have these really big electron clouds that are far away from the nucleus, and so that allows those electron clouds to polarize, to sort of shift in one direction, which results in better overlap with the electrophile during the transition state. So we can say that iodine is larger and more polarizable, which means that its electrons can move more freely towards the electrophile. So any species that is larger is going to have electrons that are less tightly held and are more able to polarize and move towards whatever the electrophile is, which results in better overlap and more strong bonding during that transition state. So as size increases, nucleophilicity increases. So the last concept is again related to size, and this is just looking at sterics. So essentially the bulk right around the nucleophilic atom. So if we think about methoxide versus isopropoxide versus tert butoxide. So here I'm going from having a methyl group to a isopropyl group to a tert butyl group, so the bulk is increasing substantially. The methoxide is going to be the strongest nucleophile, and the tert butoxide is going to be the weakest, mainly because this tert butoxide is so bulky. So the oxygen atom in each case has a negative charge, and that's the nucleophilic atom, but what's changing is the bulk that's next door. So this methoxide is going to be the best nucleophile because it's the smallest, and it will have the least steric hindrance. I'm going to say while attacking the electrophile. So the less bulk there is around the nucleophilic atom, the more effective it's going to be at being a nucleophile.